People like to say Einstein explained gravity. That's a comforting story. It sounds finished, clean, elegant. They tell you gravity is the curvature of space-time. Matter tells space how to curve. Space tells matter how to move. Beautiful sentence. You nod. Everyone nods. Conversation over. But stop and think. That's not an explanation. That's a description, a very good one, but it doesn't tell you what is happening. It tells you what to calculate, not what is doing the work. And physics, when it's honest, is not satisfied with poetic geometry alone. Take something ordinary, a rock falling. You drop it, it accelerates toward the earth. Why? Einstein says, because the rock is following the straightest possible path in curved space-time. Fine. But now ask the dangerous question, what is curving? And more importantly, how does the rock know? You're told space-time is curved, but curved compared to what? There's no embedding space, no rubber sheet in the sky. That picture people love the bowling ball on a mattress is already lying to you. That rubber sheet needs gravity to sag in the first place. You're explaining gravity using gravity. That's not an explanation. It works mathematically. It predicts planetary motion, light bending, time dilation. No argument there. General relativity is spectacular. But if you ask what mechanism makes two masses attract each other, the theory goes quiet. It replaces force with geometry and hopes you won't notice the trade. And most people don't. Because geometry feels deep. It feels fundamental. It feels like bedrock. But here's the uncomfortable part. Every other interaction in physics, electricity, magnetism, nuclear forces works by exchange. Something is transmitted, a disturbance, a field fluctuation. In modern language, a particle. That's how atoms talk to each other. That's how forces propagate. Gravity in Einstein's picture doesn't talk. It just is. No messenger, no local interaction, just a global shape of space-time that everything somehow agrees to follow. You're supposed to accept that the Earth curves space-time here, and a rock over there responds instantly to that structure, not by being pushed or pulled, but by obeying geometry. And that's where people get uncomfortable. Because the universe we actually measure does things locally, because leads to effect. Something happens here, something responds there, and the influence travels. Fields fluctuate. Information moves. There's a chain. Geometry skips the chain. Now let me be very clear before someone gets upset. Einstein didn't make a mistake. He solved the problem at the scale he was asking it. Large masses, smooth distributions. He solved the problem at the scale he was asking it. Large masses, planets, stars, light rays. And he did it brilliantly. But if you zoom in, really zoom in to where physics becomes grainy, noisy, quantum mechanical, the story starts to wobble. Space-time in Einstein's theory is smooth, perfectly continuous. You can divide it again and again forever. But the rest of physics doesn't work that way. Energy comes in chunks. Interactions come in quanta. Fields fluctuate violently at small scales. So here's the paradox. Gravity is described as smooth geometry. Everything else is described as quantum interaction. And yet gravity couples to everything. Every particle with energy feels it. There is no escape. So how does a quantum particle move through a smooth classical geometry? How does a geometry respond to a particle that doesn't even have a definite position? That's not a technical annoyance. That's a conceptual fracture. Most people try to paper over this by saying, well, we just haven't unified the theories yet, as if it's a missing chapter in a book we already understand. But you should be suspicious of that attitude, because sometimes a theory doesn't need to be extended. Sometimes it needs to be reinterpreted. And this is where I started getting restless. If every other force can be described as particles exchanging momentum, energy, information, why should gravity be the lone aristocrat, ruling by geometry alone? Why should gravity refuse to speak the same language as the rest of nature? That question doesn't come from philosophy. It comes from pattern recognition. Physics advances when one strange thing stops being special. And I didn't believe gravity was special. I believed geometry was hiding something. Not wrong, not useless, just incomplete. And once you accept that possibility, once you stop being hypnotized by the elegance of curved space, you're forced to ask a different question. Not what shape is space-time, but what is actually being exchanged. That's where the story really begins. If you're asking the right question now, it sounds something like this. If gravity isn't geometry, then what is it doing instead? Good. That's the right kind of discomfort. Because once you abandon the idea that gravity is merely the shape of space-time, you're forced to confront how every other force in nature actually operates. Not metaphorically, mechanically. Electric forces don't curve space to pull charges together. They act through fields. Magnetic forces don't rely on global geometry. They propagate influence locally. Nuclear forces don't whisper instructions into the universe's shape. They exchange momentum through quanta. So I asked a very simple, very irritating question. Why should gravity be different? That's not a philosophical question, it's a technical one. And it has teeth. In quantum electrodynamics, the theory that explains light, electricity, magnetism, we don't say particles follow paths and curves something. We say charges interact by exchanging photons. Virtual photons, most of the time, you never see them directly. But you can calculate their effects, and the calculations work ridiculously well. So imagine doing the same thing for gravity. Instead of saying mass curves space-time and objects obediently follow geodesics, you say this. Masses interact by exchanging something. A quantum, a carrier, a disturbance in a field, call it what you like. I called it a graviton. Now, before you get excited, let me slow you down. The graviton is not a little marble flying back and forth. That picture will mislead you immediately. The same way thinking of photons as tiny bullets misleads you. A graviton, if it exists, would be a quantum of the gravitational field, a bookkeeping device, a way to calculate how energy and momentum are exchanged between masses at a distance. Why bother doing this? Because once you phrase gravity this way, something remarkable happens. You can start using the same machinery that works everywhere else in physics. Perturbation theory, Feynman diagrams, local interactions, cause leading to effect, step by step. No global geometry required. Now here's the punchline that people miss. If you take Einstein's equations and expand them mathematically, carefully you find that at weak fields and low energies they behave exactly like a quantum field theory of a massless spin-2 particle. That particle behaves exactly the way a graviton would have to behave. Same predictions, same forces, same results. So the shocking thing is not that the graviton idea contradicts Einstein. It's that Einstein's theory secretly contains it. General relativity, when you look at it from far enough away, already knows about gravitons. It just doesn't admit it openly. It hides them inside geometry. You can calculate gravitational attraction using curved space-time, or you can calculate it using particle exchange. At everyday scales, both give the same answers. So, why not declare victory and move on? Because the moment you try to push this picture further to higher energies, smaller distances, the calculations explode. Literally, infinities everywhere. You try to compute quantum corrections to gravity and the numbers don't settle down, they don't renormalize, they don't politely cancel, they blow up in your face. And that's not a technical inconvenience. That's the universe telling you something. It's telling you that gravity, treated as just another quantum field, refuses to behave like the others. Now, here's where people usually make a mistake. They say, so the graviton idea must be wrong. That's the wrong conclusion. The correct conclusion is this. Our usual quantum tools are insufficient. Gravity is weaker than every other force by an absurd amount. So weak that quantum effects are invisible until you reach ridiculous energies or absurdly small distances. That weakness hides its quantum nature from us. But weakness is not absence. If gravity couples to energy, and it does, then it must fluctuate. And if it fluctuates, it must have quanta. There is no logical escape. So now you're stuck between two descriptions that both work and both fail. Geometry works beautifully, but only when the universe is smooth and classical. Quanta work beautifully, but only when forces are strong and separable. Gravity lives in both worlds. And this is where the real trouble starts. Because once you accept gravity as an interaction, a conversation between particles, you're forced to confront the possibility that space-time itself is not fundamental. It might be emergent. And that idea makes people nervous. Now we've arrived at the place where people start hoping for miracles. They want a final synthesis, a clean theory, a sentence that says, this is what gravity really is, and then closes the book forever. That instinct is understandable. It's also wrong, because physics doesn't end with comfort. It ends with bedrock. Let me show you where the ground actually is. If you insist on geometry alone, gravity behaves beautifully until space-time itself starts fluctuating. Near singularities, inside black holes, at the beginning of the universe, there the equations stop making sense. Curvature becomes infinite. Time and distance lose meaning. The map eats itself. If you insist on particles alone, gravity behaves beautifully until you push the calculations far enough. Then infinities explode everywhere. The bookkeeping breaks. The sums refuse to converge. The theory stops predicting. Same phenomenon. Two languages. Both successful, both incomplete. That's not a failure of intelligence. That's a signal. It tells you that gravity is not just another force inside space-time, and space-time is not just a passive stage for gravity. They are entangled at a level deeper than either description admits. People often ask me, so which one is right, geometry or gravitons? That's the wrong question. You're asking for ontology when physics offers you consistency. Geometry is a way of describing how things move when gravity is dominant and quantum effects are negligible. Gravitons are a way of describing how energy exchanges momentum when fields fluctuate weakly. They are not rivals. They are approximations. And this is where people get uncomfortable, because they want gravity to be a thing, a substance, a mechanism you can point at and say, there it is. But gravity resists that kind of reduction. You can calculate it as curvature. You can calculate it as exchange. You can predict eclipses, orbits, redshifts, time dilation, gravitational waves. All of that works. What you cannot do honestly is tell a story that replaces gravity with something simpler. That's not because we're lazy. It's because explanation has a flaw. At the bottom, there's bedrock. The universe appears to have a rule that energy affects geometry, and geometry affects motion. Whether that rule is implemented through smooth manifolds or fluctuating fields depends on how closely you look and how hard you push. And if you ask why that rule exists, you've gone past physics. That doesn't mean the question is stupid. It means it belongs somewhere else. Physics answers a different question. What happens if, not why does reality choose this option instead of another? Einstein gave us a language where gravity disappears as a force and reappears as structure. That was revolutionary. But structure alone doesn't tell you how reality updates itself locally. It doesn't tell you how fluctuations behave. It doesn't tell you how gravity participates in the quantum noise that fills the universe. I tried to push it there, not because I thought geometry was wrong, but because I didn't believe it was the end of the story. And I still don't. But here's the honest ending, the one people rarely like. We do not yet have a complete theory of gravity that is both quantum and geometric at the same time. Anyone who tells you otherwise is selling you a slogan. What we do have is something more important. We have consistency checks. We have overlapping descriptions. We have predictions that match reality to extraordinary precision in their domains. We know where the theories work. We know exactly where they break. That's real knowledge. Understanding in physics is not about telling a story that feels satisfying. It's about being able to say, if the universe behaves this way, then this must happen next, and being right. Gravity, whether you draw it as curved space-time or exchange it as quanta, obeys rules. Those rules can be tested, measured, trusted. That's not a failure to explain. That is explanation. You want gravity to be a picture. The universe gives you equation. You want certainty. The universe gives you limits. And if you're honest, really honest, that's not frustrating. That's beautiful.